Okay, so again, we have x-axis in terms of x, y-axis in terms of y. X-axis is your upper function minus the lower. Y-axis is really the right function minus the left. So looking at example 2 here, with respect to your x-axis, my area, so with respect to y, this integral, what's my top function here? X equals y squared. Now, in terms of x means that whatever I need to put into my integral needs to be in terms of x. So I can't put y squared in here. Rather, I need to figure out what this is in terms of x. So how would I solve for y here? What would I need to do? Take the square root of both sides. So really what I have is y equals plus or minus the square root of x. But since we're in the first quadrant, we're dealing with just the positive values. So really, we're just looking at y equals the positive square root of x. Now, if I look at my bottom function here, it's already in terms of x. It's already solved for y equals x squared. So again, with respect to the x-axis, my top function is this blue line, which is the square root of x, minus the bottom function. And the bottom function is y equals x squared, so minus x squared. And again, this is dealing with in terms of x. And again, this idea is the area between the two curves. Is what I'm doing is finding the area under this top curve and subtracting from there the area under the bottom curve. That leaves me with this region that I am interested in. Okay. Now, if I did this in terms of y, with respect to y, it's going to change things up a bit. So again, if it helps you turn your paper 90 degrees counterclockwise and think of it that way. Or look at your function, it's the rightmost function. So from the right to my integral. What is going to be my top function or the right function for terms of y? The x squared function, right? That would give me this area. So on and so forth. And then from there I'm going to subtract the bottom or the left function. And the leftovers would be that 3 in between. So when I do my integral here, that right function is y equals x squared. But we need to be in terms of y. So I need to first solve for x here, so I have it in terms of y. Same idea. Take the square root of both sides. I get x equals plus or minus the square root of y. Again, we're in the first quadrant, so we only have to worry about the positive square. Okay, so that right function is the square root of y. And that's my top function, if you will. So my left function or my bottom function would be x equals y squared, so minus y squared. And this is in terms of y. So just make sure as you're setting these up, you get to actually choose whether you want to do it with respect to x or with respect to y. For some problems, it's going to be easier to do one over the other. For some, it's going to be necessary to do it in terms of y. But whichever method you choose, make sure that your setup here, notice it's dx, and so each of my functions have x in terms of x. Down here, it's dy, each of my functions are in terms of y. So just make sure you don't have a mixture of the variables within them, because it's with respect to that certain variable you chose. And again, regardless of which method you choose, you should get the same answer. It's just another way of finding that area. Okay. Questions so far? Okay. So here we have another example. If we do this with respect to the x-axis, they didn't give us x and y. Let's call our red one here the top one. And let's go with h of x. We haven't used that yet. And let's call this other one here, the blue one, k of x. Okay, so again, with respect to x, what is my integral going to be? What's my top function? The be h of x. Very good. So my top function is h of x, and thus my bottom function is k of x. This is with respect to x. Now, when you take your paper and you turn it 90 degrees counterclockwise, if we try to do it with respect to the y-axis, let me draw it here. So if I try to go this way with respect to the y-axis, notice that my top function and the bottom function are actually the same function, right? And what we have is that when we think of it in terms of y, would you agree that this is technically not a function because it fails that vertical line test? We've turned it. So it's not a function. We can only integrate when it is a function. So here would be an instance in which you would not want to do with terms of y, because we cannot integrate, because the top function minus the bottom function, it's going to just give you 0. The same function minus itself is just 0. And we clearly have area here. Now, if you wanted to go hog wild crazy, you sure could do top function restricted by the axis here, and then double that and do the same thing here. But this would be a problem where it would be a lot simpler just to do with respect to x. So our top and bottom function here end up being the same. Go ahead and write this as top and bottom function are the same function. So we don't want to integrate with respect to y. We want to integrate with respect to y. Again, if you really wanted to, you could, but you'd have to use that y-axis x equals 0 as your bottom function, and then you would have to double that area since it's metric there. But this would be an instance in which it would be much better to just go ahead and use with respect to x. Alright, now when I'm doing my integral here, let's go back up to the x-axis. Before, in our very first example, we were bounded by some x values that were given to us. We were bounded by x equal to a and x equal to b. In fact, here, you'll notice that your bounds were a and b, because those were the x values from which we're going to. But now for this problem that we're looking at, it doesn't tell us from an x equal to an x equal. So what we're doing is this region bounded by the two curves, so it's really from this intersection point here to this intersection point here. When we have two functions, how do we find what those intersection points are? Say, what do you say? Set them equal to each other, substitute. You could do elimination, whatever you need to solve for them. Substitute one equation into the other and solve for where they're equal. Take a trip back to Algebra 1. I kids did this a couple units ago. So you would have to substitute and solve to find your intersection points, but that's what we would have to do. Very good. All right, let's take a look at this one here. All right, so again, let's go ahead and label this. I know you don't have colors, or it's not printed out in colors. So let's call this green one here. We'll call this x. And my red parabola, let's call g of x. Okay, so again, with respect to the x-axis, my area, let's go ahead and attempt some intersection points here. We're not going to go too exact. I'm not going to make you actually figure out the equation of the curve. That could be a fair problem, where you'd have to figure out your equation of your parabola and your equation of the line, and then find the intersection points in there. But let's just make it a little bit simpler. What does it look like this intersection point is? What's the x value there? Do you agree with -1? So that's -1 something, and then would you agree that this one's at 2, 0? What does that look like? Let's call this one -1 and 3.5. Let's look at it. -1, -3.5. So when I do my integral here, if I'm doing with respect to x, I use my x values. It goes from -1 to 2, so those would be my bounds. And which one is my upper function, my top function? Good, f of x. And my bottom function would be the g of x. So f of x minus g of x, and it's all of this with respect to x. Now again, let's take our paper, turn it 9 degrees counterclockwise, or just think of this in terms of the y-axis. Can we do this one with respect to y? No, one yes, one no. I got another yes, and now it changed to no. Let's take a look at it. Here, would you agree that red is your top function? But then once we get to here, so red is top, green is bottom. But when we get to here, red's top, but what's your bottom? Red again, right? So this last little piece here, it ends up being the same function for both top and bottom, right and left. So this would be another instance in which we can't do it with respect to y. Alright, well, we could, but it's more work than we really want to. So same function on top and bottom, or left, right, I guess we should say. Same function. Don't do with respect to y. Alright. Now again, we could up until, so this region we could do just fine with respect to y, but down here we would have to do again with respect to the x-axis, or sorry, the y-axis.
You are Megan. Thank you, dear.
Alright, so again, we could do this top part with the respect to the y-axis, but this bottom part we would have to do with respect to y bounded by x equals 0 and then double. So again, more work than is necessary, just do with respect to the x-axis. Okay, now something I do want you to take note of here is that when we're finding the area between the two curves, we don't need to worry about the fact that it's below the x-axis or above the x-axis. The integral by itself, before when we were finding the area underneath the curve, for example here, with respect to the x-axis meant that if it was above the x-axis, it was positive. And if it was below the x-axis, it was negative. Now, when we're looking at with respect to two different functions, the fact that it's above or below the x-axis does not give us issues with positive or negative. Basically, if it's in between your two curves, it's positive. If it's area outside of your two curves, it's negative. So when we're finding our area, because what we're having happen here is, again, we're finding the area of this top curve and subtracting from it the area of this bottom curve, so that we're left with just this region here. So it takes care of it even if it goes into the negative or below the x-axis. So I'm trying to think of a good example here. Let's go through this. Alright. If I were to find the area of this curve here, let's just say this is y equal to -1. And, oh no, this is y equal to parabola facing upward, shifted right, let's go with 2. And down, let's say 2. Okay, so if I find the area of this region here, what we're really saying is that it would be this top function, y equals -1, minus this bottom function, which ends up being that parabola of x minus 2 quantity squared minus 2. Right, it's that top function minus the bottom function. So here we have, this is my top function, this is my bottom function. So what happens when it's all below my x-axis here? And I'm going to try to explain this as best as I can here. So the area of this first line, the red one here, my first function, the area of that curve would be anything right here. Okay, so that's a negative area, just with respect to the x-axis. When I do the area of the parabola, all of this is the area of that parabola with respect to the x-axis, which is also a negative value. But since we are subtracting that area, minus the negative gives us, for this, is going to be a positive area. So we actually have this is positive, but then this piece that we had above is still negative. So the positive take away that negative, we're left with just this region here, and it ends up being overall positive. So you don't need to worry where it falls, whether it's above or below the x-axis. The equation set up the way that it is will take care of those negative areas. It will take care of that and will give you that result. And again, if it's in between the curves, that should be a positive area. So you would actually end up with a positive area between these two curves, even though it is below the x-axis. Does that make any sort of sense at all whatsoever? A little bit. Okay. All right, so let's actually take a look at doing these ones. Alright, so example 5 says find the area bounded by y equals x squared plus 2, y equals negative x equals 0, and x equals 1. So I want you to go ahead on your paper and sketch this region, sketch these graphs. So go ahead and graph your parabola, your line, and your vertical lines there. So we should have a parabola, so x squared plus 2. So this is probably where you want to use some colors to help you distinguish. Now, on the AP exam, unfortunately, you can only have a pencil and a blue or black pen, so you don't get to use all kinds of fancy colors. But I think it'll be helpful now as we start out. So this is a parabola shifted up 2, and so it's going to look something like this. And then this is a line with a negative slope. Oh man, mine's not turning out so good. It looks so much better on my paper. Oh, that's okay. I thought they were going to intersect. Alright, and then I'm going to use the same color for these because these are kind of my bounds. Same idea there. So x equal to 0. And x equal 1. Alright, so if you want to shade it in, or use a highlighter or some other color, kind of shade in your area that we're looking at. So it says find the area bounded by these. So it's the area created with all these graphs here, all these lines here. Okay? Doesn't it look beautiful? It looks so innocent. Okay. So if we look here, we could do with respect to the y-axis, but that would look kind of weird. I would definitely recommend doing with respect to the x-axis. Nothing crazy, pretty normal. Here's my top function, here's my bottom function. So there's nothing that's pushing us towards with respect to y, so just stick with respect to x. Alright, so my area is going to be the integral. Now, what is my starting bound, or my lower bound? What's my x value for my lower bound in my integral? 0. And we're going from 0 to 1. And then again, we want to do top function minus bottom function. So which one is my top function? Good. The x squared plus 2. And from there, I want to subtract my lower function, which would be negative x. Now, it is really important that you use parentheses for that second function, because you're subtracting that. If there's more than one piece, you're going to distribute that negative. And again, we're doing this with respect to x, so make sure you have the x there. It is absolutely vital that you have that part. Alright, and now we just simplify and integrate. Yes?
If you forget parentheses like around the entire sentence or like brackets, if you actually say that
Brackets are fine. I sometimes use brackets. Now, if you forgot these but still the dx, I think you're probably still fine. I think it's assumed that anything between here and the dx is a part of it. Technically, though, you should have parentheses around the whole thing. But I don't think on the AP exam they would take you off or take off if you did not have parentheses around the whole thing. I believe there are issues, though, if you don't have the dx. Alright, so let's go ahead and simplify and integrate this. So 0 to 1. And we would get x squared plus x plus 2. Do we agree with that? Just make it simplified. Okay. So then let's go ahead and integrate this. So we have x cubed over 3 plus x squared over 2 plus 2x evaluated from 0 to 1. And then we just go ahead and evaluate. So that's 1/3 plus 1/2 plus 2 times 1 minus, if I take 0 and put it in, all of that is indeed 0. And then we simplify from there. Let's see, probably going to comment it under 6. 2, 6 plus 3, 6 plus 12, 6. 17, 6. Do you agree with that? So that area between the two curves is 17/6. And again, what it really is this area is positive and this area is added to it. It's kind of that idea of total distance traveled. Kind of like that idea. Questions on this one? That was too easy. Let's try this one. Find the area bounded by y equals 4x minus x squared and y equals x. Alright, go ahead and graph this, see what you get. Use what you know from previous years to help you sketch these graphs. What type of graph is this for you? It's a parabola. And what else do I know about this parabola? It's negative. Good, so it's going down. Typically, knowing our x-intercepts, our zeros, are helpful. What would be my x-intercepts for this? If I factor this out, so I have negative x times x. This would be another way to write it if I factored it out. What would be my x-intercepts there? That gives you a pretty good idea. It's going to then be upside down through here. And with all parabolas, your vertex is halfway in between. So really, you could find this point, take 2. If you wanted to, take 2 and substitute it in and find that value. It doesn't have to be perfect, but use what you know about those graphs to help you sketch it. Okay, do you get a graph that more or less looks like this? Okay. So the area bounded by these two curves. So you're looking for the area enclosed by those two curves. Be careful. You're not choosing this. That's bounded by your x-axis of this curve. So you want the area directly in between those. So it's this area here. Okay. Now, from graphing, we were able to actually find one of our intersection points. It's not always going to necessarily be that easy, but we do need to know this other intersection point. Depending on how you graphed it, you might be able to figure it out from your graph, but for those of us that didn't make it exact, we need to find our intersection points. So my intersection points is where the two functions occur at the same time. Right, so it's where my green function equals the red function, so where 4x minus x squared equals x. See that? We're just taking our two y's and setting them equal to each other. Right, and then we go and solve. We're going to have to factor since it's x squared and x. You want to keep your highest power positive, so I'm going to go ahead and move everything to the right side. So we get x squared minus 0. I can factor out that x. So we should get intersection points of 0 and 3. And if we look at our graph here, that seems to make sense, right? So I'm going to go ahead and label those intersection points. 0. Now, if we're going to do this with respect to x, we don't really have to know the y value here. Sometimes it's helpful, but since we're going to do this with respect to x, we don't really need to know. All right. So now we can go ahead and calculate our interval. So the area equals, now that we know our bounds from 0 to 3, and again, it's just top function minus bottom function. So my top function is this green one, negative x squared plus 4x. Or you could have just written 4x minus x squared. Oh, actually. So that's my top function. Minus my bottom function. My bottom function is just x. And the whole thing with respect to x dx. Alright, I trust that you guys can integrate this, so I want you to go and simplify it, integrate it, and get it down to one single number. You guys get 9 halves? Awesome. Good. So 9 halves is right. Alright, any questions on that? Oh, good. Something even more interesting. Okay. So here, find the area bounded by these two curves, and now we have a cubic function and a parabola. How nice. Again, these don't have to be perfect, they don't have to be beautiful, but you do want to get an idea of what's happening. So, actually, before we sketch this, so we know that my f of x is a cubic function. So we know it's going to have some type of squiggle, and since this is positive, we should have the right side is going to positive infinity, the left side is going to negative infinity. We can find our x-intercepts from here, right? How do I find my x-intercepts? Yeah, set it equal to 0. So I have, let's go and factor out an x. X squared minus x minus 10. Ooh, we can do some factoring. unfactor all factor, and let's see if we get the same thing. And then once you do that, go ahead and factor your other one here. If I look at this function, this is a parabola, but notice we have that negative in front, so it's going to be an upside down parabola. But again, you're going to want to find your zeros, your x-intercept, so go ahead and set it equal to 0, solve, and see what you get. And then I want you to go ahead and sketch these to the best of your abilities. And I don't know how high or above or how far below it goes. Again, it's just that sketch. We've got that cubic function that is positive, right side's leading towards positive infinity. We have those x-intercepts that we found. And then here I have an upside down parabola. 0 and 2. And let's just do this. Now, do you agree at some point in time these are going to intersect? Okay, so I'm going to exaggerate mine a little bit more to see that intersection. I don't know exactly where it occurs, but just for my visual sake, I'm going to go ahead and make it occur a little earlier. Okay, so somewhere around here. Right, so we have for sure these bounds, but we need to figure out what this one is. How can I find out when this occurs? You can plug the x value back in, but do I know the x value at which it occurs? I don't even know the x value. So how can I find that x value at which it occurs? Substitution elimination. We have that this is y equals, so set them equal to each other. So let's go ahead and find those intersection points. We'll from there probably go ahead and get our other two that we know, but let's set them equal to each other to find our intersection points. So our intersection points so we have our f of x function, 3x cubed minus x squared minus 10x should equal negative x squared plus 2x. And then go ahead and move factor and solve. Cubed, my x squareds end up canceling. Minus 12x equals 0. Factor out my 3x, so I have x squared minus 4 equals 0. Oh, difference of squares! I love those. So we have our intersection points are 0, 2, and negative 2. Do we agree with that there? So we had already found the 0 and the 2, but now we know that the other intersection point is at negative 2. Okay, so if we look at the region bounded by these two curves, do you agree that it's actually these sections, not just this section, but also this one here? Right? We actually have two regions here. So the area bounded by these two curves are actually these two regions. Now when we think of, so again, this is probably going to be best to do in terms of x. We have no issues with it here where it overlaps on ourselves. In terms of y, it would overlap on itself, so let's just do it in terms of x. But take a look at your top function, your bottom function. Notice what happens when we go from one area to the next. It flip-flops, right? So I want you to go ahead and try just setting up your integral. You're going to have two different areas, two different chunks. I want to see, can you set up your integral as needed? I want you to go and try setting it up. See if you can figure out how to set up your integral to find these two areas. Ooh, forgot to label my intersection. So this was -2 something. This we know is 0, 0. And this will tell us 2, 0. Okay. Alright. Let's see how you did with your integral. So my area is going to be, for this region, it's from -2 to 0. My green function is the top function. So my green function was f of x. I'm going to go and write it first in terms of f of x, g of x. Minus g of x. And then I can add to that the other integral. So from 0 to 2. And now my top function is g of x. And my bottom function is f of x. Yeah. So I have two regions. This first region goes from x equal to -2 to x equal to 0. My top function is the green one, f of x. So I do top minus bottom.
So then why did you switch it?
So then over here, this region is from 0 to 2. Look what your top function is here. It's now the g of x is on top, so it's going to be kind of the reversal. Top minus bottom is now g of x minus f of x. That's the difference there. Other questions on that? Let's go ahead and actually set it up. I'm not going to make you go through all the math anymore, but let's go ahead and set that up with the actual values. Okay. So we have 0, or -2, 0. And my f of x function was 3x cubed minus x squared minus 10x. So this was my f of x function. Minus my g of x function. -x squared plus 2x. The whole thing dx. So that's just that first region. And I add to it the second region, which was from 0 to 2. And my top function now is -x squared plus 2x. Minus my bottom function here is your 3x cubed minus x squared minus 10x. Again, the whole thing with respect to dx. Alright, any questions on your setup there? Thank you. You guys need to stop sneezing. Okay, I want you to go ahead and simplify. Don't integrate yet, just simplify. Distribute that negative, simplify. I want to see that we get the same thing. The trickiest thing here is most students miss that negative with the parentheses. Okay, do we agree with this? 3x cubed minus 12x, and then your other one's -3x cubed plus 12x? When we distribute out this negative, my x squareds end up canceling. I get a negative 2x to be combined with my negative 10x. Over here, I get that negative 3x cubed. Again, your x squareds end up canceling. And then you end up getting positive 10x to combine with 2x squared. Alright. Now, for sake of time, I'm not going to make you actually go through and integrate each individual one. I trust that after that last test, you can indeed integrate. But say we were to actually go through and do this after a good amount of work, I believe, if I have the correct answer here, it's 24. So write that somewhere in your notes on your own time. I'll let you go ahead. Shouldn't be too bad. Alright, questions on that? Okay. Oh, we're not to the trig yet. Okay, so taking a look at this one. Find the area bounded by x equals 3 minus y squared and y equals x minus 1. This should concern you that one is in terms of x and the one's in terms of y. This is a little radar that you might have to consider with respect to y. It doesn't automatically mean that, but it's a very good possibility. Any ideas what this graph looks like? It's a what? I only see this, but I can't actually. The eyebrow thing? Oh, like this? But on one side? Okay, so square root, kind of like a square root curve? Okay, good. So would we agree that it's like a parabola turned on its side? Okay, kind of like half of a parabola, or half of a hyperbola. Okay. So let's go ahead and investigate what this looks like. For terms of graphing, it's probably easier for us to think of this in terms of x. Okay. If you recognize that it's that sideways half of the hyperbola, that's great. Alright, so here we have, if we actually solve for y, then I would have y squared equals negative x plus 3. Right? Let's subtract 3. So this is going to indicate that it's going to look like a parabola but turned sideways. If you don't catch that though, you can still take the square root of both sides. You're going to have y equals plus or minus the square root of negative x plus 3. But to think in terms of transformations, I'm going to go ahead and write this as negative of x minus 3. Right? All I did was factor out a negative. This helps you out in terms of transformations. So we have the positive square root and the negative square root. What does this negative inside indicate? Oh, it's reflected which way? So this way? This way. So if it's with your x, it affects your x's, which means they all go negative. So it was a sideways parabola, now it's turned facing this way. And then which way has it shifted? To the right 3. That's why I went ahead and factored out that negative, because now we can see that's actually to the right 3. Yes, Marcus?
When does it flip over there?
When it is outside of your square root. So like y equals negative of the square root of x, you would take this and flip it upside down. So if it's grouped with your x, it affects your x's. If it's outside of your x, it affects your y's. Alright, so a rough sketch of this. Okay, so the rough sketch is going to be, again, sideways parabola, flipped across, and shifted right 3. We know it has that square root idea, so over 1, up 1, over 1, 2, 3, 4, up 2. Mimic that on the bottom. Something like that, right? Sideways parabola, reflected and shifted. Again, from here you might be able to recognize what that is. Okay, and then this one, thank the Lord, is a lot simpler. So, line ourselves to negative 1. Okay. So our region here, okay, orange juice. Go home and drink some orange juice. You guys need to get healthy again. I don't like you all being absent and sniffling and sneezing. You say it's the heat?
In here.
Oh, in here. Well, that's possible. Okay, so we agree this is the region that we're looking at. Okay, so now let's take a look at this. If I do this with respect to the x-axis, so vertically, if I try to do this vertically with respect to x, what is my issue? Why not, Parker? Good. On this chart right here, the top function and bottom function are the same. That's an issue. So now let's consider if we go the other way with respect to what? So horizontal. Oh, looky there. It works so much nicer and never overlaps on itself. So this would be an instance in which with respect to y is actually the preferred method you want to use. Now when we do with respect to y, we're going to use the bounds of y. If it's respect to x, the bounds of x, respect to y, the bounds of y. Same idea, it's just now everything's in terms of y. Okay, so we need to find our intersection points before we can actually calculate it because we don't know our bounds. We find our intersection points by, well, can we set these ones equal to each other? Really? If you solve for one first. Good. So we want to substitute. I'm going to go ahead and take this guy, put it in for x. All right, so for my intersection points, I have y equals x, which is 3 minus y squared, minus 1. Again, I want to go ahead and factor to solve. Let's move my y squared to the left, so everything to the left, so I get y squared plus y minus 2 equals 0. This factors into y plus 2, y minus 1. So I get y equals negative 2 and y equals 1. Which, if we look here, that makes sense. We can pretty easily find our x values. If I take negative 2, put it in minus 1, that would be negative 3. And if I take 1 and put it in... Oh, I'm sorry. I did that wrong. This is my y value. Put it in for y. So I'd have negative 2 equals x minus 1. Add the 1, so you would get negative 2 plus 1, negative 1. Right? Do we agree with that? You guys are staring at me. Okay, hold on. These are my y values. My y equation. So if I want to solve for x, take negative 2, put it in. Add my 1. So I get x equals negative 1. Do you see what I'm doing there? We don't. I just want you to know. So, yep, Sarah's correct. We don't need the x values because we're doing it in terms of y. But should we have needed them, that's what you're doing. Okay, Noah, what's your question?
I understand why we use substitution to solve for this problem, but with like a more complicated equation, why wouldn't we solve it the same way we did before, where we set the two terms equal to each other?
So the reason why we could set those equal to each other here was because it was y equals y equals.
But we moved this so it was one. So
We could move it. Yeah, we could move this so that it's...
we were correct.
Oh, yeah, I guess we did. Yeah, we could have done that.
Is that just more complicated than it has to be?
It might be. It ends up giving you squared there. It's probably about the same amount of work. Yeah, you could have done that. I don't... When we have pluses and minuses in front of the square roots, I don't like that part. Which it's still fine, you square it, the plus and minus go away. But yeah, you could do that. I guess I did make you do more work than you had to. That's okay, it's good. Builds character. Okay, so does the heat of the tree. Alright, so again, we don't need to have our x's here, but again, it's good for you. And this one, when we take 1 and put it in, we get 2. Okay. But as Sarah said, we only need the y value since we're doing it with respect to y. Okay, I think we're going to go with our function now. Okay, we're doing it with respect to y. So just like x, we went from the lower value to the higher value. With y, we go from the lower value to the higher value. Again, we're going with respect to y. So my lower bound would be negative. I wrote them backwards, didn't I? Thank you. Glad we didn't get any further with that. That would have been much better. I'm sorry. What was it? -1, -2? And I'm not going to be able to fix that. And this one was 2, 1? Okay, thank you, ladies. Alright, so setting up my integral, my y values, -2 to 1, like we found over here. So -2 to 1. These are my intersection points, which is why I'm choosing them. Now my upper function, the top function, in terms of y, is that right side function. So what would be my function I'm using here for my integral? Good, very good, Parker. It's 3 minus y squared. Again, I want it in terms of y, so I want where it has y. We solved here to be able to graph it, but since I'm doing it with respect to y, I need to see y's in my equation. So this would be 3 minus y squared is my right function, that top function. And then my left function, or that bottom function, would be the other one, x minus 1, but we need it in terms of y, don't we? So I've got to rewrite this in terms of y. So x equals y plus 1. Do you agree with that? Yes, Marcus.
Why is bounds wider than
Why are they what?
-2?
It's my y values. It's the y values of your intersection points. If you did what I did, I wrote my intersection points wrong. So your y values are -2 and 1. Does that make sense? Okay. Alright, so my right function, 3 minus y squared. My left function, or the bottom function, would be y plus 1. So it's this minus y plus 1. Notice your parentheses are huge here, because it's minus of this entire bottom function. Again, before you carry on, your with respect to should match what variables you have in here. If you had a mixture of x's and y's, go back and fix it. Notice we are with respect to y now, not with respect to x. Okay, questions on our setup here? Okay, carry on. -2 to 1. So we'd have, distribute that, -y squared minus y plus 2 dy. Do we agree with that? Okay. And then again, you would integrate it, yada, 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 so on and so forth, and we get, in the end, 9/2, once again. Okay. Questions on that? Okay. Finally, trig. I feel like I should read a Shakespeare ballad or sonnet to this. How beautiful thou art, O trig, manometry. Alright, find the area bounded by f of x equals 2x sine x, or 2 sine x, and g of x is tangent of x. You get to go back to, isn't it like October, November where you learn how to graph these things? Of pre-calculus, so like a year and a half ago. Travel back in time. A blast from the past, as glorious as it is. Alright, so we're dealing with trig. Typically we have our axis is pi, 2 pi. Notice though our bounds, we're actually not going that far. So I'm just going to draw it to pi. And what can you tell me about my sine x function here? What does that 2 do? Okay, it stretches it vertically, right? It gives it an amplitude of 2. So that means that up here I'm going to want to have 2, not just 1. pi. This is negative pi. Alright, let's see how well you remember your sine and cosine. Sine, does it go through your origin or is that cosine? It goes through the origin. Good. Sine of 0 is 0. If you need to think back to your unit circle, 1, 0, 0, 1, negative 1, 0, 0, negative 1. This is 0, this is pi, this is 2 pi. Cosine, sine, alphabetical. Alright, so it goes through your origin. What's sine of pi over 2? 1. Since it's an amplitude of 2 though, that means it's 2. Comes back here. Continues on. Same idea over here. Continues on. Okay. So again, it continues on, but we're interested in just a smaller region of negative pi over 3 pi over 3. Alright. Tangent of x. They didn't even mess with it at all. I feel a little deprived. Okay, so tangent, cotangent, we know it has that weird squiggle. Is it this way? Is it this way? There's asymptotes. Which one is it? So think back. Tangent is the same thing as sine over cosine. So tangent is going to go through 0 since sine goes through 0. Alright, it's sine over cosine. So whenever sine is 0, tangent's 0. Alright, so now we've got to figure out where our asymptotes are and so on and so forth. My asymptotes are when cosine was 0, because that's what makes our denominator 0. Cosine normally looks like this. So since cosine is 0 here and here, that's where your asymptotes are going to be. Okay? So I have my asymptote over here. Pi over 2. If you think of your unit circle, 1 over 0. Alright, now we gotta figure out which direction is it. So let's think of pi over 4. What is tangent of pi over 4? Positive 1, right? So somewhere around here. Same idea for negative 1. So we've got our tangent graph with something. Oh, these are always so hard to draw. Something like that, right? Okay, so that region in between are these tiny little slivers. Oh wait though, didn't they say only from negative pi over 3 to pi over 3? Is that here? Is that passage? Do we actually have a little sliver beyond there? Is it before there? Let's see. So our intersection points are where they're equal to each other, right? Where they cross each other, where they intersect. So it's where f of x equals g of x. So our intersection is really when 2 sine of x equals tangent of x. Now, at this point, we could suspect that perhaps the reason why they gave us this is that these are the intersection points. You could solve for it here. You should probably confirm that, though. Let's just suspect and substitute in. What is sine of pi? Let's start with pi over 3. What's sine of pi over 3? Square root of 3 over 2? Okay, I think I heard that a couple of times. Good. So if I did f of pi over 3, would you agree that is 2 times square root of 3 over 2? So that's really just square root of 3, right? Okay. Tangent of pi over 3? What's tangent of pi over 3? If this is the point 1/2 square. What is tangent of this? Root 3. Yeah, it's root 3 over 2 over 1/2, which becomes just root 3. So that actually is the intersection. Okay, so this is actually when x is pi over 3. And something else. And I'll save us time. Same idea down here. if you were to go ahead and solve this, you could subtract your tangent, so you have 2 sine of x minus tangent, which is the same thing as sine x over cosine x, 0, factor out a sine x, and you'd have 2 minus secant x equals 0. This is when sine x equals 0, and when secant x equals 2, and you end up getting these 3 values. This is when x equals 0, and this is when x equals pi over 3, and any variation of that, which is also 0. Okay, so you end up, if you actually were to solve it, you would get that. Okay, enough of that. Let's do this. Oh, looky there. Don't we have 2 different regions and the top function flip-flops? So we have from negative pi over 3 to 0. What's my top function here? The red one, which was tangent. So tangent of x minus the 2 sine x dx. And then we add that to our other region, which is from 0 to pi over 3. And now my top function is the 2 sine x minus my tangent of x. Do you know the integral of tangent of x? No, some weird natural law thing, right? Probably would need a calculator for this. When I did it with some crazy decimal, I can do it again. I did not write it down. So use a calculator. This will be on a calculator section. And after I pass out your homework, I'll calculate what it actually is. What do you think is true about these 2 regions? They are the same. So it's going to be double of just the one region. So it's the same thing as twice just one of them. If you think about it as that odd function type thing, all that. Okay. So remember next class, bring back that calculator form and bring 4 AAA batteries because you have to provide the batteries for those calculators. It will not come provided for you. And your homework is this coming back to you.